Okay, so in this video, we're going to compare linear regression to logistic regression. And one of the big differences between linear and logistic regression is the loss functions we derived in the last video. So the loss function for linear regression is the mean squared error. The mean squared error, so it's this formula. Let's copy and paste it from before. It is this thing. That's the thing you're minimizing. And in logistic regression, you're minimizing not the mean squared error, but this crazy looking cross entropy loss. So I'll copy that over right here. Okay, and this is the cross entropy loss. Okay, I guess it doesn't need a name. Let's write cross entropy loss. And just before we dive in and figure out exactly what's going on when we do these things, let's get a little visual. So let's go back to our data. Data. Okay. So here is our green data is this Gaussian stuff, and our blue is the Bernoulli type stuff. And linear regression does what it sounds like. It tries to fit a line. So you try to do a line of the form y equals ax plus b, and I'm going to add parameters a and b. And what you're trying to do is you're trying to find good values of the parameters a and b. Let's make this a dotted line. A dotted line. So I guess the slope should be positive here. And let's try to move it over like this. And the slope has to be... Okay, ax plus b is being a bit annoying. Let's do ax minus b. And then I can make the slopes a little bit better. What slope do I want? I want a positive slope, and then I want b to be around here. And so you can sort of do this by guess and check by hand. And if you have this mean squared error metric, you have a notion of what values of a and b are better than others. So you can try to find the best possible value of a and b in this thing. And the best possible value of a and b is the one that minimizes the mean squared error. So that's what's going on. In logistic regression, again, what we're trying to do is we're trying to fit to this kind of thing. And instead of using y equals ax minus b, we have something very similar. And we're still using some linear stuff, but we're using this sigmoid function. So this is the function s of x, which is e to the x divided by 1 plus e to the x. This is the sigmoid function, and it looks like that. And if you take the sigmoid function and you feed in a linear function into it. So if I do s of cx minus d, so I have a linear function cx minus d, and I'm doing the sigmoid applied to it. Now when I mess with these things, I'm moving around where the sigmoid function is, and I can try to say what is a good value to put there. So what are good values of C and D? And I will measure how good I'm doing. How good is the blue curve matching the blue data? I will measure it with the cross entropy loss. All right. So that's what we're doing. That's like the high level. The only reason this video exists is to show you a cool miracle that happens. So with the Gaussian formula, so the formula for the green curves and the lines, it's not hard to believe that everything is just linear algebra land. It's all very simple. Nothing super complicated happens because I have a line that's like linear. I have the squared, which is like the norm. And so that's very linear algebra flavored as well. And so everything goes together and everybody's happy. It's just linear algebra. So it works nicely as you would expect. For the blue line though, look, I've done a bunch of crazy stuff. So first of all, I have this crazy cross entropy formula. This is like an insane formula, right? Like it's got logs and all this like funny stuff going on. And as a second crazy thing, on top of this craziness, I have added a second layer of craziness, which is this insane sigmoid function, s. This e to the x over 1 plus e to the x function that is doing some crazy nonlinear stuff. So I have craziness on top of craziness. And you might think, okay, well now you're double screwed. Like you're never going to be able to do anything. But it turns out these two crazinesses cancel out. The craziness of the sigmoid curve exactly cancels out with the craziness from the cross entropy loss. And you end up with a very nice formula that looks almost identical to the Gaussian case, to the ordinary linear regression case. So that's what I want to show you here. And again, I'm just doing this in the simplest possible way to kind of like motivate what's going on. And it works for, you know, multiple, if you have multiple covariates instead of just one, like in this picture, and all the nice things about linear regression. But let's see the math. Let's see how it works. Okay, so to start with, what I'm going to do is I'm going to compute what's going on when we try our model function. So our model function, and our model function tells us that we're going to try a function of the form, it's going to be linear. So what does linear mean? It's going to be a sum, and it's going to have a parameter beta for every possible input of x. So I'm going to call it beta j x j. So here I'm thinking of the input x as being a vector in Rn. In the plot I showed, right, in Desmos, it was just R1. So there was only one x, but in general, there are n of them. Oh, I should say m, right? So m. So n is the number of data points. Maybe this is a good thing to add. Number of data points. That'll be n, and the dimension of the data. Dimension of the input, or the covariates, that'll be m. So each xi is in r to the power m. Okay, so this is my formula for my estimate. It's a linear combination of the components of x. If you want to add an intercept, you can just make one of the components 1, and that'll add it in. So again, we got to be careful here because we got x subscript I, and we also have x subscript j, and they mean two different things, right? So I mean, this subscript I means the ith data point, and this subscript j means the jth component. So this is a possible confusion, but from now on, I'm just going to think of only one input. Only one input. So I'm just going to fix some x and see what happens with only one point. And then at the very end, we can generalize it to endpoints. And that's because we're operating on whatever is going on inside the sum. The sum itself isn't actually hurting anybody. So we're going to do it all for one point x and see what happens. So here's our model function mu. And I'm going to derive the sort of the update, or the like kernel of the update formula for linear regression. You're going to see it's all very linear algebra. It's all very nice. So we have this mu hat. All right. And we have the loss function, which I said is the mean squared loss. And so what I'm going to do is I'm going to do the derivative of the loss with respect to parameters. Parameters beta. Beta j. So I'm going to do, we're going to call this thing the mean squared loss. That's the loss. And once you have, so the loss actually depends on whatever estimate mu hat you had. But if mu hat is itself a function of all the betas, so some people write this as mu hat of x semicolon beta. So it depends on the x's and the betas. Then the loss function is a function of the betas. So the loss function is a function of the betas, right? Because I'm thinking of one fixed data input x. I have one input x and output g. So the loss function only depends on the betas. And so what is it? It's just this formula, x minus g minus hat mu of x semicolon beta all squared. And again, it's very easy to generalize to the sum, and we'll do that at the end. But it doesn't change anything. It just makes the notation harder. So I'm going to leave it out for now. We're going to do one data point. And so if you want to write this out explicitly, what is it? It's g minus the sum j equals 1 to m of beta j times x sub j. So the jth component squared. All right, so yeah, just be really careful. This xj is not the xi from over there. I don't know what the right way to do it. Should I do 1 comma? Yeah, okay, let's put the sum in everywhere, just so that people don't get confused. Let's I'm gonna take back what I said earlier. Let's put the sum in, and so this possible thing, so this is xi, gi, and then here we have gi xij, and I'll just be very explicit, and we'll do it a little slower, and leave it all in. Okay, so the loss depends on the betas. If you know the betas, then you can figure out this loss function. So it depends on the loss and the data that you have, but we're thinking about it only as a function of the betas. So if you want, we can do like the loss as a function of the betas given the data, right? g and x's. But we're thinking about it, how does it depend on the betas? And we're trying to minimize it, right? We're trying to find the betas that minimize this. We're trying to find the values of the slope and intercept for the line that make the loss as small as possible. And so the way to do that is to take the derivative, right? You want to minimize a function, you do its derivative. Okay, so actually let's make this one, this is explicit loss. And what is the derivative? So that's the derivative with respect to some special j, let's call it j star. Okay, actually, I think we can just say beta j and it'll be okay, of the loss. So what is the derivative? You got to do the derivative of this function. Okay, but this is everybody's favorite function to do. What's the derivative of something squared? Well, it's 2 times the thing. So what's the derivative of g minus mu hat squared? It's gi minus mu hat of xi given beta. The derivative of the squared function is just, the derivative of x squared is x. The derivative of the squared function, you just delete the 2, move the 2 in front, and you're done. Now you got to do chain rule. So then you got to do the derivative of, with respect to beta j, of this mu hat function. Okay, but mu hat is linear, so the derivative is, again, very easy. What is the derivative with respect to beta j of this function? It's just the jth component. So you can also see that here. You could have done the derivative sort of explicitly from this thing as well. But in either way, it's chain rule. So very simple answer. Times x j. xi comma j. So it's the jth component of the ith data point xi. And so this is a very super simple formula. Didn't take a lot to get to. And it is actually very interpretable. So what it's saying is, when we want to update this thing, we want to decrease the loss. So we can update, one way to do it is something called gradient descent, where you update the parameters beta according to their gradient. If the gradient is very large, you want to do a big update. That means that changing it just a small amount will make your loss a lot smaller. And if it's small, you want to just change it a little bit. So in general, you always change in this direction, in the derivative of the gradient of the loss. That makes the loss as small as possible. Okay, actually you go down by the loss, so it's gradient descent. And this is saying the amount you should change it, you take how far g is from our current estimate, and then you multiply that by, you weight it by xij, by how much of the j is appearing in the x. So it's a weighted sum of the difference between g minus mu hat. It's like incredibly simple, right? So if g is it's like an underestimate, if g is way bigger than mu hat, then you need to go a lot in that direction. If g is approximately mu hat, like you're already there, then like you don't need to change much. So this formula, g minus mu hat, very easy to interpret how far you are from the actual thing, and xij is how much of the component is appearing. So very interpretable, and makes a lot of sense. So you can do this with gradient descent. It turns out that because mu hat is also just this linear thing, you can also solve this directly with linear algebra. So you could set this derivative equal to 0, and you would get a big matrix equation, and you would solve it. But even before that, I think this formula is really intuitive and makes a lot of sense. So it's a good one to know. We're gonna show this is what we're gonna fill in. We're gonna fill in a whole bunch of work here, and there's gonna be more steps. And there's gonna be this like miracle fact that we start with the ugly cross entropy loss, and we start with the ugly sigmoid. But at the end of the day, they're gonna cancel, and what we're gonna get the exact same formula, except instead of mu hat, it's going to be p hat. So this part is going to be way harder. This formula, that's going to be way harder. But the final answer is going to be the same. Is that when you are doing logistic regression, you have the same kind of thing as regular regression for the loss. So when you're doing updates or something, it's again exactly the same interpretation. You look at how much of an over or underestimate the thing is. So going back to our picture, you would just look at, am I overestimating or underestimating every single point? And that will pull on the parameters, right, by a weighted sum. So very simple to interpret. The thing that is not so simple is how we get here. So over here was 2 lines. It was like do the derivative of squared. And here you're going to see there's quite a bit more work. But that's what I'm going to do in the rest of the video, is I'm going to fill in this extra work. So n and m, this is the same as before. Okay. So this part is a copy paste. Only one input. I'm going to do that again. And that's going to be the same. Now we are not doing mu hat. Now we are doing p hat. And I'm going to write p hat. I'm going to write it as sigma of hat mu. So I'm going to reuse the same function mu as before, because we know what that is. It's just this sum, but we're applying the sigmoid function to it. Okay, and I need to do it like this. Okay, and then maybe I'll add a line for the sigmoid function. Sigmoid function, and it's this function sigma of x is e to the x divided by 1 plus e to the x. Okay, so what's going to happen? We got to do the loss function, and remember it's a different loss now, so that's why things are going to be uglier. But the loss function is this guy. Okay, and there's a negative sign that's wrong here, but this is the loss function. The loss function is a function of the betas, and it's equal to, I guess I want it like this, this whole guy. All right, p hat, instead of thinking of it depending on the x's, I think about how it depends on the betas. So it's p hat of x comma beta, and this thing p hat comma beta. All right. So you're given some data. Let's say you're given the x, the b's and the x's. So you're given this data, all the blue dots, and you want to come up with this thing. So we're playing with these parameters, and we want to know what's going on. All right. So yeah, you're playing with these parameters C and D, and you want to know what's going on. Okay. All right. So this is our formula. Now we got to take the derivative, right? So take the derivative, and you can see it's a lot more complicated because we have this ln function in the way. We have p hat. We have sigma. Oh my god! But we got to do it. So let's do it. So first we'll do the derivative of the logs. So that part is okay. So what's the derivative of log? It's the reciprocal function. So we have bi. What's the derivative of log? That's 1 over. So it's hat p of xi semicolon beta. Then I have another fraction, 1 minus b. Then the derivative of log is 1 minus hat p of xi semicolon beta. All right. Now I got to do chain rule. So all of this gets multiplied by the derivative of the inside. The derivative of the inside is p hat for both hat. So it's the derivative di beta j of hat p. Okay. I did one little cheat here, which is that I took the derivative of 1 minus p hat. What's the derivative of 1 minus p hat? Well, it's the derivative of p hat, but with a minus sign. So to fix this, there should be a minus sign right here. Okay, maybe I did some sneaky derivative tricks. This is like first year calculus. How do you do the derivative? But this is what I came up with, and I think it's right. Okay. Now we got to do the derivative of p hat. Before, that was easy. The derivative of mu, super simple. Now it's complicated because of the stupid sigma function. So now we're going to do chain rule one more time. So let's add some lines here, and we're going to do chain rule again. So we have this crazy thing, and p hat is actually mu sigma of mu, where sigma is the sigmoid function. So when you do the derivative, you got to do one more chain rule. So you get sigma prime of mu, of hat mu of xi semicolon beta. And then chain rule, last chain rule of the day. Then we got to do the derivative of mu hat mu of xi semicolon beta. Okay, and we're running off page here, so let's add a line, and actually let's make can we make this column a bit wider for us? That would be nice. Okay, so made it a bit wider. Now we all fit. So we did chain rule one more time. all right, now we're like, how are we making any progress? How on earth are we going to get to this simple thing? Just like some insanity that needs to happen. And the insanity that happens is a nice formula for sigma prime. So if you try to work out sigma of x is this, if you try to do the derivative of sigma to get sigma prime, you can try to do it. You can do it by quotient rule, derivative of the top, derivative of the bottom, etc., etc. And you do some more stuff. You will eventually find that the derivative can be written as sigma x times 1 minus sigma of x. So in other words, it can be written as e to the x over 1 plus e to the x. And 1 minus sigma of x is the sigmoid's evil twin, 1 over 1 plus e to the x, right? So you will eventually find, after you do the derivative, and a bunch of cancellations, so it involves the fact that the e is nice, that this happens. And so this really is fundamentally the reason that the sigmoid function is so nice, is it has this nice formula for derivative. The derivative of the sigmoid is itself times 1 minus itself. And you can see this visually. So let's just get a whole new Desmos. So s of x, the sigmoid function, is e to the x divided by 1 plus e to the x. All right. And I'm claiming its derivative is something. So Desmos knows how to do derivatives, so it did quotient rule and it figured out the derivative is this blue curve. I'm claiming that's the same as s of x times 1 minus s of x. So blue curve, green curve, blue curve, green curve, they're the same. So that's like the miracle that happens, that these two things are the same. I guess we can make one of them dotted so you can see. Okay, let's make this one red. We got nice like Christmas colors over here. They're the same curve, and it really just comes from some miracle property of the sigmoid function. This is why the logistic function is so important, is because it does this. Okay, so how does that help us? Well, if we use this fact and we plug it in right here where we have sigma prime, what do we get? Okay, all this stuff is the same. And then sigma prime, I just said sigma prime is actually sigma times 1 minus sigma, right? And let's make the brackets a little bigger, 4, to help us out, times all this stuff. Okay, and what gets inputted here, so it's sigma of whatever this stuff is, so let's put that in. That's mu of all this thing. Almost out of room, but okay, look, I promise things are gonna simplify, because sigma of mu, we have a name for. Sigma of mu is what we're calling p. So this whole thing, the sigma of mu's are simpler than they look. They're just p's. This is just p. I'm going to delete everything here. We just have p. And over here, delete everything. This is just p. Look at that. Okay. And then we have the derivative. All right, so I guess we need even more room. Let's make the column even wider. If it'll let me. Okay, well, it will not let me. Give me one sec. Okay, I'm back. I made it a little wider. So what have we done so far? We've taken the derivative. We used chain rule. We used sigma is 1 minus sigma. And now we're ready for some miracle cancellations that really come out of nowhere that shows you how the sigmoid function plays nice with the cross entropy function. So we have p times 1 minus p over here. We have p and 1 minus p over here. Okay, these really are p hats. Let's put the hats back in. P hats. And they cancel out. So you have p hat on top, p hat on the bottom. 1 minus p hat on top, 1 minus p hat on the bottom. So when you cancel it out, what are you left with? Is some nice stuff. So the p hat on the bottom goes away. So you just have bi. But then you got to multiply by this other guy, 1 minus p hat. So if we bring that guy in, it'll look like that. And similarly over here, we got 1 minus p hat on the bottom. 1 minus p hat on the bottom. We got 1 minus bi. The 1 minus p hat on the bottom cancels out with this term, but we're left with a p hat. Okay. And the derivative of mu, right? That was the same derivative over there. That really is just xij. Xij. How much of j is appearing in the ith example? Xij. Okay. All right. We're so close. So what do we have? If you simplify this guy, a miracle happens. So you got a b, right? B times 1 is b. So let's copy this, and we'll do the cancellation. Okay, b times 1 is b, so there's just a b. But then you have b times p, right? So we're going to b times p, bi times p. Over here you have minus p, so minus p hat, and then you have minus b times p. That's a plus b times p. So it looks like that. All right, and look, that's the thing. This is the miracle. Minus b and plus b, they cancel. So you get exactly what I claimed is on this line. Okay, there's a negative sign. This is I probably forgot the negative sign or something. Where did the negative sign come from? Negative p. Yeah. Okay, it's because this is not the derivative of the likelihood. This is the derivative of the loss, which is the negative of the likelihood. So these negative signs should all be gone. Let's fix that up. Negative signs all gone everywhere. In the same way, there was no negative in front of this one. Okay. But look, we finally did it. So it's this crazy fact that the sigmoid cancels out with the cross entropy loss. So you end up with a beautiful formula when you're doing logistic regression that looks just like ordinary regression. So, and that is why people use logistic regression. It just works so nicely. And it has all of the same kind of feeling as regular regression, right? You're estimating the probability p instead of the mean mu, but everything works exactly the same. You have the same kind of formula that is easily interpretable and works really nicely when you're doing things like gradient descent or other ways to optimize this. So you can't do linear algebra because p hat is maybe more complicated than mu. It's not just has that nonlinear thing to it, but this works really well and super easy to implement and run. Okay. So I'll leave it at that. This went a little longer than I thought it would, but hopefully that helps you appreciate why logistic regression is so loved.